Okay, well, good afternoon, everybody. My name's Chris Percival, and I work for Smiths Group here in London. I'm Group Head of Excellence for the group, and very, very engaged in our own journey to net zero, and also our adjacent sort of opportunities in the hydrogen and carbon capture space. So I have a personal interest in this topic. What we're going to do this afternoon is we're going to have, I think, 3 speakers who are going to present views around hydrogen at work. That's the theme, for about 10 minutes each, and then we're going to have a moderated discussion which I'll lead. So without further ado, I'd like to ask Phil Caldwell to come up, please, from Ceres. Thanks, Phil.
Good afternoon, and thanks everybody for attending this session, and thank you to Bosch for hosting this event. I've been working in hydrogen and fuel cells for almost 20 years, and where we are now, for me, is unprecedented in terms of the scale of the opportunity and the demand for this technology. And the underlying reason for that is exactly what's on this slide. We need hydrogen for a net zero future. We cannot achieve net zero without having hydrogen in our society. The beauty of having this slot is we've already heard from a number of speakers this morning, and there's a large consensus of opinion of where hydrogen plays. I'm Chief Executive of Ceres, and we're very passionate, obviously, about this topic. We're a purpose-driven organisation. Our purpose is really to deliver technology that enables clean energy globally. And we do that through partnerships with the world's most progressive companies. Obviously, Bosch is one of our partners, but we work across many industries and many sectors from a global point of view. And that's because the urgency of the issue requires us to act at scale and pace. And that's going to be a key theme. This is not just a UK problem or an issue, it's actually a global issue that we have to collaborate on to address. There's a lot of talk, obviously, going on in Glasgow right now. 1 minute to midnight, keep 1.5 alive. This is really quite an interesting chart. If you look at the trajectory that we're on, there's a small dip during COVID on our carbon emissions, but where we actually are is nowhere near the 1.5 degree pathway. Now, if we start to accelerate beyond that, we could maybe achieve between 2 and 3 degrees temperature rise, which is still pretty dramatic for our society. And that's fundamentally because I don't actually believe that we're acting at enough pace, at enough scale to decarbonise all sectors of society. So we can make a lot of progress on some of the easy to electrify parts of society, but this is really where hydrogen comes in. To use the beer analogy, hydrogen reaches the parts other technologies can't reach. Hydrogen allows us to address parts of society that we can't directly electrify. If you look at carbon as a very simplistically, just over a third is heat and power in our homes and buildings. A third is in industry, and there's been a lot of talk about hydrogen's role in industry this morning, and we'll talk about that in this session. And then another 25% is on transportation. If you look at this chart very simplistically, the grey areas across these sectors of industry, transport, building, heat and power, and prime power and heat. The grey area is where we can go directly with electrification. And with the black is electrification with batteries. The blue area of this chart, the light blue area, is where hydrogen plays. And you can see hydrogen plays right across society. And the dark blue is the hybridization, where it's complementary to batteries. So batteries and fuel cells, batteries and hydrogen. So just going left to right, decarbonization of industry needs hydrogen. If you think about steel, ammonia, cement, that part of society. Transportation, the lighter end of transportation, we can get there with batteries. I drive an EV, it's a great product, but we need more infrastructure. But as you go heavier with power density, you need to start to hybridize. And then ultimately, the last speaker and earlier speakers, there's the really hard to decarbonize parts of society. Aviation's going to need synthetic fuels with hydrogen as a precursor. We're working on shipping both on the fuel cell side and also looking at future fuel compatibility with things like hydrogen and ammonia, where that's going to come in the future. These hard-to-abate areas need to be addressed now, because if you think about the challenge to decarbonize shipping towards 2040, 2050, we're going to have to bring technology on at scale and pace and actually introduce it. We're talking about major infrastructure challenges here. And then the far right, there was the topic this morning about building heat and power. New builds, sure, you might be able to directly electrify, possibly using heat pumps, etc. But actually, for a lot of us, we're going to have to use the technologies that we can in our existing buildings, which are far from energy efficient. So again, existing residential, commercial, there's going to be a role for fuel cells and heat and power in this sector. And then finally, probably the one we can decarbonize most directly with electrification is our power grid system. But again, there's a role there for long duration energy storage, potentially using hydrogen and fuel cells around peak power. So you can see there isn't one solution to this. We are going to need all the tools in the box, all the technology that we have, but there's a big role for hydrogen here. That amounts to potentially 18% of primary energy coming from hydrogen. And that's a big opportunity. That's a $2.5 trillion opportunity. And that's not just a UK opportunity. That is a global opportunity. So where does Ceres fit in? Well, we are world leaders in electrochemical technology, and I say that with some pride. And we enable the world's most progressive companies to adopt technology at scale and pace. And this is what this is about, because sometimes people say, well, do we need a lot of innovation to get to this net zero future? Well, no, actually, these technologies have been around quite a long time. You know, the technology that we have, we've been perfecting over the past 20 years. But it takes partnerships to really accelerate that, particularly when we're faced with what is fundamentally an existential crisis. We've got to bring this technology through at pace. And we say we're world leaders in electrochemistry. Well, what does that mean? Electrochemistry, for me, is a bridge, as in we can go from electrons to molecules and molecules back to electrons, and that's really powerful. So fundamentally, if you have a green electron from renewable energy, you should use it where you can directly, but very often you can't. So if you need a green molecule, which is a precursor to a synthetic fuel, or to be used directly in an industrial process, electrochemistry can turn a green electron into a green molecule. And vice versa, if you put that molecule through a fuel cell, you can generate green power the other way. So one of the beauties of the Ceres technology is it's truly reversible. So we can go both ways. So we have a proprietary solid oxide cell, a steel cell, which was actually invented next door at Imperial College, only 100 meters from here. And if you run it in one direction, we can use multiple fuels to generate power highly efficiently, all the way through to zero carbon. So we can run on natural gas today. We can run on blends of natural gas. As was mentioned this morning, you can already run on 20% hydrogen in natural gas now on our products. They're also hydrogen compatible for a hydrogen future. And also we can run on future fuels like ammonia, which are going to be used for things like decarbonisation of shipping. And on the top here, you can see examples of the systems we've developed with global partners. So our technology is now on sale in Japan with Miura, one of the leading industrial boiler companies here. With Bosch, obviously, needs no introduction, and we're going to talk more with Wayne about that in the next presentation, our collaboration there. With Doosan in South Korea for stationary power and shipping, and with Weichai in China on automotive applications and stationary power. But also, if we run this in reverse, we can actually use it to generate green hydrogen. And the picture on the bottom is the megawatt scale demonstrator that we're building now that will show the potential of this technology to produce very high efficiency, low cost green hydrogen. So the same technology can go forwards into power or the other way into green hydrogen. Technology alone is not enough. I'm very proud of what we've done at Ceres, but even with the team we've built, which is 500 people, we are now leveraging partnerships. So we have a big team now working with Bosch. We have big teams in South Korea with Doosan, with Weichai in China. So we get scale through partnerships. So our ecosystem is growing. Obviously, from the UK base, Bosch, our big partner in Germany, Weichai in China, I'll talk about it later on, Doosan in South Korea, Miura in Japan. And we see this as a growing ecosystem of partners that can all license our technology to address this huge opportunity. So if we talk about the first application, which is heat and power in commercial buildings in society, what we've done with Bosch is we've taken the core cell technology, and in collaboration with Bosch, we're industrializing that for mass production. So you take the cell on the left, we build it into 5 kilowatt stacks, and there's one of these upstairs. And you may have seen the unit on the way here today. You then build it into 10 kilowatt power units. Those units are more efficient than any thermal-based combined cycle gas turbine power station. So we go from fuel into power out at over 60% efficiency, and in a system that's hydrogen ready. And here's a picture of the fuel cell in real life in Bamberg. I understand this is actually at the bus station next to the pretzel shop, so apparently you can get zero carbon pretzels right now, if I understand it. But the big thing on this is we're working with Bosch, where we've transferred technology, and Bosch are now producing these fuel cells in Germany and looking to scale to 200 megawatts. I also mentioned some of our other partnerships here. Here you can see a 10 kilowatt system we've developed with Doosan in South Korea. They're now looking at going into higher power, into hundreds of kilowatts, and also into megawatt scale. So South Korea is one of the biggest shipbuilding nations in the world. They have a partnership with Hyundai Heavy Industries looking at applying solid oxide technology for auxiliary power and even prime power propulsion of shipping. So another big part of society that we need to decarbonize, this technology can address directly. We've got a very strategic partnership with Weichai in China. They may not be a household name to you, but they are the largest combustion engine manufacturer in China, the world's third biggest commercial vehicle manufacturer. You cannot ignore China. China is 30% of global carbon emissions. But the other interesting thing about China, if you look at history, look at what China has done in terms of solar, in terms of batteries. They know how to scale, they know how to mass produce, they know how to get down cost curves, and it's a huge market opportunity for us. So China is a key part of this global issue of how do we actually get to a net zero future. Earlier this year, we took the decision to essentially double the size of the company, and we're moving into green hydrogen through electrolysis. To do that, we're committing 100 million to the development of megawatt scale, high efficiency electrolysis. One of the criticisms sometimes of electrolysis is its low efficiency. With solid oxide, we could be 20 percentage points higher into the mid-80s to 90% efficient, particularly if we can do industry coupling. Now, what's interesting about this is we believe we have a pathway to $1.50 a kilo of green hydrogen. And that's really where green hydrogen starts to be very competitive with blue and grey hydrogen. So that's key. There's another interesting thing about this is to do this, we actually raised 180 million in the public markets in London. And we were 3 or 4 times oversubscribed. So now you are actually seeing, I think Mark Carney talked about it yesterday, there's a change of finance now coming into low carbon technologies. We're not short of opportunities here, and the good news is that the financial sector is also now wanting to invest in companies like Ceres for this kind of future. But the topic is hydrogen for work. We believe that with the move into electrolysis, we start to address the other part of society that we hadn't touched before, which is industrial decarbonisation. If you think about steel, that's 7% of carbon. Ammonia, which is about 2% of carbon. industry overall 24%. So really, that's our objective, is how do we decarbonise all sectors of society? So just to leave you on this, we're very proud to be a UK company. And there's been a lot of talk today about how do we scale and level up in the UK. The UK is also a science and technology powerhouse. We've invented some of the world's best technologies that we've all relied on for most of our lives. The same thing can happen again with hydrogen and fuel cells technologies. We invent and innovate this technology, and through global giants, we actually can scale at pace and bring this to society for all of our benefit. Thank you very much.
Well, thank you very much, Phil. I'd like now to ask Wayne Kern from Robert Bosch to talk about collaboration with Ceres. Thank you. Thanks, Wayne.
So, Phil, great pictures. There was one picture missing. It was you and me signing a similar contract like the wage hike guys did.
I wanted that, and I didn't have it.
I could have sent you before. So, Wayne Kern, nice to meet you. I'm extremely thrilled, to be honest, to be in that industry. I was 20 years with Bosch in different sectors. And in the last 4 years, I actually joined the activities towards stationary fuel cells. And why I'm thrilled, I actually going to run through that. Let me give that with a picture. I got a 4.5-year-old daughter. And when she's in my age, that's the time we have to run. And how often do you have really in your life the chance to do something to make that world a little bit better? And I think we will actually do that. And I know we are heavily investing. So, is the clicker working? There we go. So, what brought us to stationary fuel cells? And let me start a little bit different. I'm not starting with hydrogen. I'm starting with electrons. So with a very long study which we actually did, we saw that the electrons are increasing heavily for the next years. So just last week, actually 2 weeks ago, the German Electricity Net Agency actually projected that just in Germany, the electricity consumption will increase between 30 to 40% compared to today until the year 2035. And at the same time, Germany going to shut off 50% of the electricity production because we are getting out of nuclear, roughly 10%, and another 40% on coal-produced electricity. So why is electricity increasing? It's actually here on the side. Well, one is we are heavily going towards electrification in the cars. I guess that's pretty clear. But not only cars and trucks, but also trains. Still roughly 40% of the trains in Europe are still running on diesel engines. If you look at the worldwide, that's actually more than 60 or 70%. So a huge electrification in terms of mobility, increasing electron. The second thing is what we call urbanization or electrification of life. We heard about heating, like heat pumps before. We know our own life actually, how that actually develops, increasing there as well. And there's something which we call digitalization. And most people don't know. If you're actually thinking about what does digitalization means, you're talking about data centers at the end. And it's not your iPhone, it's actually a data center where everything happens. And if you put already today all the data center of this world in one country, this country would be behind China, the US, behind Japan, and India, already the 5th biggest energy consumption country of the world. Or in other words, the internet consumes roughly 1.5 times the electricity of a country like Germany with 80 million people. And this is before digitalization really starts place, right? I don't see any drones working already. I don't see automated driving yet. Okay, Industry 4.0 topic starts and so on. So huge electrification on this one. So now Wayne talked about a lot of electrification. Why the heck is actually the hydrogen coming in? Well, very easy. At Bosch, we do not believe that an all-electric world for 100% will happen. Phil, you mentioned it before. We also believe that there will be 15, 20, 25% of electricity needs to get stored for storage reasons, for import reasons, for actually getting it from somewhere else, and to secure your electricity grid also in moments when the sun is not shining and the wind is not windy. And that is actually the reason why Bosch decided to invest into, decided to invest into 2 big areas on fuel cells. On the left side, we have seen already this morning, heavy investment on the mobile part. We invest heavily into PEM systems over there. And on the right side, actually into solid oxide fuel cells. Why did we choose Ceres Power as our corporation? I actually come in a second, because we think that the technology that Ceres Power developed together 20 years first at the Imperial College and then 20 years at Ceres himself does have some huge advantages that really can make a big impact. So what are we doing? Bosch just announced roughly half a year ago that we will invest more than €1 billion into the fuel cell activities until the year 2024, 2025, to go for industrialization of two topics, stationary and mobile. You see downstairs one of the stationary systems. We already have more than 100 systems running to create fully connected data, which we can then actually get back into the development progress. We have started 3 years ago with 8 employees at the 1st of January 2019. We are more than 500 people end of this year, so we take that extremely serious. We have chosen the production sites at Bosch that perfectly fit the competencies levels. We have great partnerships. Ceres Power is one. We got multiple other ones with component suppliers, because we also want to be an OEM at the stationary side with a full system. So we need blowers, inverters, pipelines, all that stuff, helping a transformation of a machinery and an automotive industry, taking the competencies into the next level. We invest just on the stationary side roughly 400 million, our own investment, and we've roughly invested 150 million euros into Ceres Power. So altogether, a little bit more than $1 billion I'm allowed to spend being the commercial responsibility within the next 3 or 4 years. So why are we actually investing into that? Well, very easy. We got a production plant in Bamberg with roughly 6,500 people working on exhaust systems, on spark plugs, and on actuators. So lambda sensors, actuators, and spark plugs. That is ceramic know-how by its best. And you do need to industrialize the Ceres technology know-how that much into actually ceramic components. On the other hand, we're actually welding exhaust systems for the automotive industries in a plant which is close to Hamburg. So you need to know a lot, or you need to have a lot of know-how if you want to actually industrialize so-called hot box systems. At the other hand, we are using the Salzgitter plant because there we are building roughly 30 million ECUs, so electronical units, to actually steer cars in this case, but steering a car and potentially steering a fuel cell, that should actually work. And then at the very end, Bosch is also, we have heard this quite a few times, one of the biggest thermotechnology companies. So we're using there the know-how of a system integrator of Bosch Thermotechnology. And now comes the topic why we have also won already not only 1 or 2 prizes, but quite a few. We're not thinking about only putting single units out there. First of all, obviously, you can put them into a cluster. But there's one thing, and I'm going to touch this also in another slide. Each of these units is already today 100% connected in the cloud. So if you have a so-called digital twin in the cloud, you can connect the single digital devices in the cloud as a virtual power plant. Or in other words, to extract it easier, you can have 5 of the units downstairs in your wine cellar, 10 at the roof of your building, and 5 at the corner of the street, and they are all operating as one large single electricity production device. And there comes one other topic into it, and I mentioned the data center topic, or actually the internet topic. When everything gets more connected, the availability of electricity increases, as important as it is today in a hard transportation center in a hospital. And if you cut the very large centralized power plants into multiple hundreds and potentially thousands of small devices, you get a security grid you have never seen before. So by single devices, highest efficiency possible, large corporations, we think we're going to have one corner, one pillar to the energy transformation. And as I said, we're not doing this alone. We said we are checking, we thought about it doing it alone, and we must say, I think we found a perfect partner, which we're working now for 2 years, 3 years, very intensively. We worked with them a little bit beforehand, also for a lot of testing topics. We are helping each other at the moment from a more prototype development into a large manufacturing device, and Ceres Power is adding more and more ingredients and new technologies into it, and we take the competencies to industrialize it. That's the stack collaboration we actually have. On the system side, as I said, we go our own ways, but they are collaborating with a lot of component suppliers out of the automotive industry, the machine industry, the electrical industry, and so on, to really pull the whole industry actually out of the water. So what does a single device actually do? And I think people that are here, you can actually have a look downstairs. The very interesting one, why we also invested into SOFC, is it's fuel flexible. I don't have to wait that there is a hydrogen world in probably the age when my daughter is 40 years in decentralized application. But I can plug it into the national grid at the moment using natural gas, using biogases, using hydrogen, or all admixtures of that. And if you do so, and just a few numbers on this one, if you do so, we would reduce the CO2 emissions in the electrical grid in Germany by roughly 40% right away using natural gas. 40% just by accident is also the number the German government wants to achieve in the year 2035. So run on natural gas is definitely also a bridge. Phil, you have shown the bridge. But on the other hand, it's also a road afterwards, how the future can actually get much, much better, but with an immediate impact and not a waiting time for the next 10 years. That's also why I don't want to argue where to use the hydrogen first. Please not really use it potentially in every single decentralized application. You can use it for steel industry, you can use it for airplanes, you can use it for fertilizers and so on, but I have an immediate effect with a technology that is hydrogen ready. And then when the hydrogen kicks in afterwards, when countries like Chile, we heard Saudi Arabia, we heard Australia and so on, really kicking up also with importing possibilities to us. So just in very short, the electrical efficiency is the very best you have ever seen in this world. So we are producing at the moment on the prototypes, that's not the finished final developed product, an electrical efficiency higher than 60%. A combustion engine normally has what? 20 to probably 30%. That is doubling the efficiency on the electrical side. And at the same time, I still have about more than 200 degrees of off heat. And in decentralized location, I can easily use the off heat. And Phil, you mentioned about the pretzels. It is real. Like we are heating the bakery, and at the same time, we take the electricity and actually giving to a more family house. So it's sector coupling as its best. So extremely high efficiency, 85, almost 90%. You hear nothing. The sound and the vibration is probably the sound of the vibration of an old washing machine of Bosch, which is 10 years old. So you don't need to have any isolation, no vibration, nothing. We have absolutely no measurable NOx and particles coming out, even so we run the system with natural gas. So also there, I always say, you don't put a combustion engine or a CHP next to the kindergarten of my daughter. I lived in China 4.5 years myself, so I know what particles are. But a fuel cell, no issues at all, even so if it runs on natural gas, because no particles, much better on CO2, bridge technology, and long-term actually future. Perfect. What do you really want more? So in a nutshell, what we have decided was we go very fast into public with the units. Why is that? We want to have, or we will have, a manufacturing output of 200 megawatt in the year 24-25. That is just around the corner. We have already produced more than 1 megawatt with units already running with CE certification. We put them in the field, even so they're partly still prototyping. Phil, you mentioned the bakery. We got other topics in a container. We got other ones in the Salzgitter plant, putting them under real case conditions and not into a laboratory. And why not in laboratory is also very easy. A technology like this was never developed before. And if I would put it into the laboratory and I have my engineers walking around with a candle every day, you guess what happens? Nothing. They would never fail, they would run perfectly and so on. But putting them under real case conditions, that's really the know-how I get. And that's why we are developing such a unit in such a speed, because we're taking real-time data, fully connected devices with real-time customers, and we put it into the development cycle. That's how we do it. Very, very uncommon also in Bosch, but that's the only way how we want to be, and we can be fast. Everything else takes 5 years longer. We take a big risk, but we think invented for life is the slogan at Bosch, and this is, what is it, right? That is invented for life at its best and as possible in the fastest pace you can do. So join us in that energy transformation, and thank you very much.
Okay, thank you very much. Thank you, Wayne, for that presentation. I'd now like to call on Paul Martin from Spitfire Research, please.
Hi, everyone. Saying hello from Toronto, Ontario, Canada. And I'm speaking on behalf of myself and my little consulting company, not on behalf of any client or employer. Today, we're going to be talking about decarbonization and where, if at all, hydrogen fits into it. So what we hear in the media is that hydrogen's perfect. It's the most abundant element. You can burn it in a fuel cell and you get nothing but water. It's the Swiss Army knife of energy. And what you hear again and again and again is that it's perfect for the hard to decarbonize sectors. But of course, that begs the question, why are we not working on the easy to decarbonize sectors first? I have no problem with hope. Okay, I don't hate hydrogen. I've worked with hydrogen for 30 years, making and using hydrogen in synthesis gas. I don't hate hydrogen. I just think it's a really poor choice as a fuel. And I'll explain to you why. And I caution people that there's been a lot of talk that's really forward-looking statements and hope. And there's nothing wrong with hope. Hope is great, but hope has to be set within the limits of thermodynamics or it's false hope. So what is hydrogen? Hydrogen is, in fact, a decarbonization problem that we've barely begun to solve. It is not really a decarbonization solution to much of anything. So let's explain why I think that. First off, we make an awful lot of it right now. We make 120 million tons of it per year. 96% of it is made from fossils without carbon capture. A little bit, 4%, is made by accident as a byproduct of chloralkali manufacture, and maybe about 2/3 of that is made from fossil-derived electricity. So what you're left with is that 98.7% of hydrogen in the world right now is made from fossils without carbon capture. And there really isn't any green hydrogen to speak of in the world right now. The other thing to keep in mind is that when people make hydrogen, they use it right where they've made it. They barely move it any distance at all, and that's for good reasons associated with the properties of the molecule and its thermodynamics. So when we look at hydrogen as a system, one of the use cases is to try to use it to store electricity. So you feed either methane or electricity and water into the front end, and you feed it to a device like a steam methane reformer or an electrolyzer. And for the most part, you throw away about 30% of the energy. And then now you have hydrogen, you have to compress it or liquefy it or make something else out of it. And depending on which of those you do, you're going to lose another 10 to 30 or 40% more. And then you feed it to a fuel cell or a turbine or an engine, and you lose a bunch more. And round numbers, about 50% is lost there. If you take 60% as that final, and you have no energy used for transport and just 10% used for compression, which is a kind of barest minimum, the bleeding edge best case is about 37% cycle efficiency from electricity back to electricity again. And the only conclusion you can draw from that is that hydrogen's a really terrible battery. The other use case is heat. And here you lose a little bit less because, of course, you're not trying to go backwards. You're not starting with electricity, which is basically thermodynamic work, and then making hydrogen, which is basically thermodynamic heat, and then trying to make thermodynamic work again. You're using that chemical energy as heat. So there you lose only about, 37% of the energy, but it's still not a particularly efficient way to make heat if you're starting with electricity, given that a resistance heater makes heat from electricity with 100% efficiency. Here's another key point. Of that 120 million tons of hydrogen that we make per year in the world as both pure hydrogen and in synthesis gas, about 90 of it will be needed post-decarbonization for things that we really will continue to need, like continuing to eat. An awful lot of it is used to make ammonia, which is used to make all of the nitrogen-containing fertilizers in the world that feed us. To replace that 90 million tons at a incredible energy efficiency of electrolysis of 50 kilowatt hours per kilogram of hydrogen would take 4,500 terawatt hours of electricity. And in 2019, all of the world's wind and solar combined added up to only 2,100 terawatt hours of electricity. To do that would take about 1,000 gigawatts of electrolyzers running at 50% capacity factor, which is actually pretty high when you consider wind and solar and not hybrid wind and solar. So the conclusions you have to draw here is that, first of all, there is no meaningful quantity of green hydrogen in the world. And second of all, that the notion that we're going to have excess green hydrogen to use in inefficient ways anytime in the near future is decades premature. So let's look at some of the use cases that are proposed. The first one, the most obvious one that's just a dead dog of an idea, is feeding hydrogen to cars. Here's a comparison between two cars, a hydrogen car that you can buy and an electric vehicle that you can buy. And the net result here is that the hydrogen car, it's more expensive, it's heavier, it accelerates half as quickly, it uses 3.2 times as much energy, and it costs over 5 times as much per mile driven. And what do you get in return for that? Basically faster refueling. Valuable, but I don't know if people presented with that value proposition are going to be too excited with it. And I think the sales figures more or less prove this out. The big problem, of course, is that with hydrogen as a fuel for transport, distribution cost is really high because of the nature of the molecule. Getting it around is hard, and so people want to make it on site in small equipment, which means poor capital utilization efficiency, which means high cost per kilogram of hydrogen. So not looking good for cars. Well, okay, let's forget about cars. Let's talk about trucks. Well, hydrogen's definitely possible for trucks. And hydrogen's possible for lots of things. But the thing we're trying to differentiate is between the possible and the things that are practical and economic and make sense from a decarbonization perspective with limited resources, generally government resources being used to fund the transition. So the thing about hydrogen for trucks is that electric trucks are coming. In fact, they're already here to a limited degree. And they can offer a lower cost of ownership because their energy efficiency is so much higher that they just save an awful lot of money on fuel energy. The other thing is that people often conclude that trucks have to use hydrogen because they're worried about the weight of the trucks. But in fact, when you study freight transport, you find out that most loads gross out, meaning they're limited by the volume of the load, not the weight of the load. So a little bit more weight taken up by batteries is not going to basically mean that you have to run twice as many trucks. The other thing is that when you look at trucks and the applications where electric vehicles are never going to work, so for instance, running trucks up ice roads into northern Canada to resupply First Nations communities, you're never going to use trucks for that purpose with electricity as the feed, but you're also not going to use hydrogen for those purposes because of fuel logistics. And biofuels can actually solve these fuel logistics problems and these niche cases where electric is not an option better than hydrogen can and at a lower cost. So I just don't see room for hydrogen in trucking. How about aircraft? The big problem with aircraft, again, it's possible to fly an aircraft on hydrogen. It's also possible to do short-range aircraft with batteries. But the long-range ones, the jets, hydrogen's problem is that its energy density per unit volume is far too low to be effective. And as a consequence, you have to push more volume through the air, which means more frontal area, which means more drag. So as a consequence of that, you're going to be in some trouble with hydrogen as a fuel for aircraft. And the likely option is what another speaker mentioned, which is that you're going to use hydrogen, if at all, to make fuels by taking even more of an energy efficiency hit in order to feed fuels that aircraft actually like, that are liquids. And shipping, don't ask me, I have no idea what shipping is going to do. Shipping is actually a problem for the world as far as energy, because, and I apologize for that ringing phone in the background. Shipping is a problem because shipping is a bottom feeder of the energy market. It's international. It's very difficult to regulate. So whatever decarbonizes decarbonizes shipping is going to happen last. Hydrogen to replace natural gas, similarly a fraught problem, because although 20% hydrogen by volume sounds like a lot, it's only really 6% by energy and about 7% ultimate decarbonization potential. So also not looking good. The details of my concerns about hydrogen to replace natural gas can be found in my articles, but I will try to wrap up quickly here. The big problems are that the distribution network is okay, but the transport network that carries natural gas long distances is not suitable for replacement with hydrogen. And the infrastructure replacement cost, especially for all the compressors, is extremely high. So it's possible, but not likely. This is Liebreich's ladder, which shows the merit order uses of hydrogen potentially in the future. And the ones that are that kind of reddish color at the top, they're basically existing uses of hydrogen that need to be replaced with green hydrogen. The greenish ones are things that are probably going to be done with biomass instead of with hydrogen. The yellowish ones are possibly done with hydrogen, but more likely to be done directly with electrification. And so to sum up, the meme is sufficient. Hydrogen as a fuel is the problem. Green hydrogen to replace black hydrogen is the objective, or should be the objective. We're not working on it, and it begs the question, why? Ultimately, where we'll end up using hydrogen is as listed there, to replace black hydrogen as a reducing agent, perhaps to make iron out of iron ores. If we're rich and desperate, to make e-fuels, and maybe as a niche use in high temperature heating, but forget about comfort heating. And with that, I will enjoy engaging in the conversation with the other speakers and with the audience. And I refer you to my website, spitfireresearch.com, so that you can read that I'm not just basically making this stuff up, that there's references and calculations that back up what I'm saying. Thank you very much for your attention.
Thank you, Paul. So to kick off the discussion then, really, I think we've heard from Phil from Ceres and Wayne from Bosch, who spoke largely around the progress to date and the future potential of hydrogen, and a competing view from Paul, joining us remotely, with emphasis on current capabilities and capacities, limitations and concerns. It's really, really clear, I think, to everyone that becoming net zero by 2050 will require a gargantuan effort globally over the next 30 years. And this will include a blend of renewable energy, electrification, and of course, relatively new technology like hydrogen and carbon capture. So with that in mind, I'd like to ask our speakers, starting with Phil and Wayne, where are we realistically going to see hydrogen a reality in industry? And what are the key enablers require us for us to succeed in this space? Thank you.
Okay, sure. I can kick off. It's interesting with Paul's presentation, because actually his last slide was probably more future-looking than his previous slides. And some of the things Paul had on there, I agree with. If you look at the use cases for hydrogen as a reducing agent for iron ore in steel, we've got to green steel. Ammonia, and how do we green fertilizers, and also ammonia as a potential solution for shipping. Paul said we didn't have a solution for shipping. I think there's lots of organizations, Ceres is one, is looking at decarbonization of shipping. So some of those kind of applications are where there's an obvious use case for hydrogen. And it goes to this point, if you can electrify something directly, you should. But where you can't directly electrify something, then you have to convert that energy to a green molecule, and hydrogen is that potential green molecule. Or, and I think this is something that was missing in Paul's analysis, is for synthetic fuels like aviation, etc., hydrogen is often a precursor combined with Fischer-Tropsch, etc., to actually getting into synthetic fuels or e-fuels. Now, today, some of these solutions might be out of the money. They might be expensive. But as we start to get rising carbon prices, some of them become into the money, and you have to look forward into 2030, 2040, 2050. It's very simple to be a critical thinker. I'm a chemical engineer. I've been trained that way to go, well, this is the problem today. But the urgency we need on this is, okay, let's have the solutions. And hydrogen is one of the solutions. It's not the solution.
Thank you very much, Phil. Over to you, Wayne.
Yeah, maybe, I think I mentioned at the beginning, that is a marathon we have. So, and for sure there will be different steps where the hydrogen is best used at the beginning and probably later somewhere else. I'm not a chemist, I'm not a physicist, I'm a business administration guy. So what I look is, what's the best total cost of ownership perspective? And what Paul mentioned is, for big portions, probably right, but sometimes what's forgetting is, what's the other side you can do? So if you really want to have an all-electric world using the electrons all the time, then we would need roughly 7 to 9 times the amount of renewable energies to never phase out a blackout scenario, at least in Europe, at Central Europe. So I would need to have a copper cable connection between Portugal and the Ukraine and from Scandinavia to Sicily to really outbalance the situations where I don't have wind and when I don't really have photovoltaics at the moment. And there's 2 topics coming in. One is obviously investment that needs to be done for this one, point 1. And the second one is the acceptance of the society to really have such kind of infrastructure staying in front, your family house. And we see it at the moment already in Germany that we made it possible to have, I think it was like 5 kilometers of large power net grid new investments in the last 2 years from northern Germany to southern Germany, mainly because, society doesn't accept these very large power grid systems in front of their villages, in front of their houses. And everyone is raising their hand at that time and saying, I don't want that, I don't want that, and that. So I think hydrogen is actually a topic where if you calculate all costs in and social acceptances of a society, it will play a role. Is it 10% or is it 20%? I don't know, but usually the last 20% for the decarbonization is the hardest. And I don't want to have a future where I'm ending at 80% and then ruin the world, probably not in 50 years, but in 150 years. I want to save it in total. And therefore, I think, Phil, you mentioned all the tool in the toolbox, and that is, in my opinion and my company's opinion, definitely a tool in that toolbox.
Thank you very much. Thank you, Wayne. Over to you, Paul.
Okay, so there's a fundamental notion that people use all the time, that efficiency is unimportant if things are cheap enough. And the reality is that we as humankind, we're willing to trade efficiency for greater effectiveness. And gasoline is a perfect example of that. Gasoline is not very efficient, fed to a gasoline engine. Gasoline engines are on the order of 15 or 20% efficient. But it's so effective. It's a liquid, it's easy to move around, you can pour it into a tank, it stays there for a long period of time as a stable material. So we're willing to trade efficiency for effectiveness. The trouble with hydrogen as a fuel is that it's neither efficient nor effective. So remember the very best case efficiency of converting electricity through hydrogen back to electricity again of 37%. If we involve using hydrogen to make fuels like Fischer-Tropsch fuels, and unlike the speakers, I actually do this for a living. That's exactly what I do. I help people scale up chemical process technology and design and build pilot plants, including Fischer-Tropsch and methanol pilot plants, by the way. If you involve those sorts of chemical transformations, that cycle efficiency drops from 37% to single digits. So when the argument is, well, people don't like electricity and they don't want to see electric pylons in front of their homes, they prefer something that they can ignore. The trouble is that you now have to make, if you're invoking hydrogen or especially hydrogen-derived fuels as the solution to that problem, you now have to make 9 or 10 times as much renewable electricity to solve those problems as if you just use the electricity directly. And given those sorts of choices, I just don't see them as being likely. So do I see hydrogen as having a role in the future? Absolutely it does. Green hydrogen needs to replace that black hydrogen. That's a giant problem. It needs to be the priority for solution before we think about wasting any ammonia, for instance, for shipping. we have to actually make ammonia that right now we make entirely from natural gas derived hydrogen without carbon capture. We have to make that from electricity so that we can keep eating. And that's much more important than greening shipping.
Paul, thank you very much. So we've heard there, I think, about some of the current challenges with hydrogen technology. I'd like now to ask our speakers probably a final question, because we have about 5 minutes left. Just what can governments and international bodies do to help make hydrogen a success in the future? Thank you.
Maybe let me answer that first. We had one representative from the German government or from German embassy before, and he talked about this IPCI, this important project of common European interest on hydrogen. My topic, the stationary fuel cell, we are one of these 62 projects that are actually going to get funded. So German government said, you know what, I want to invest roughly 8 billion euros. If you add all Europe together, it's roughly 35 million euros in funding, but it also unleashes roughly 150 billion of investments in total. And what the governments also do is, and this was actually pretty smart, it makes it complex, but it's smart. You only get the funding if on a European basis, at the same time, there's someone putting a solar panel or windmill, someone puts an electrolyzer in, someone takes care about the transportation, so pipelines or trucks, and someone invests at the same time for the consumption, from heating to fuel cells to mobile to agriculture and to steel, because what it actually does is it solves the chicken egg problem. And I think that initiative for this IPCI, governments do very well at the moment, at least in Europe, to solve that, because it lifts the hydrogen world at the same time over the whole value chain out of the water. So therefore, I think they're doing quite good. And obviously, there will be a bunch of regulations and so on, but this will follow actually after. The speed and the push, at least on Europe, I definitely see at the moment.
Thank you, Wayne. Thank you.
Yeah, look, I agree with that point, but I don't think it's just Europe. I think it's happening. You know, there's over 30 nations now signed up to very strong hydrogen policies, and I think we're seeing this in South Korea, in China, in Japan. So there's a global realization that it will be part of the energy system in the future. The percentage, I mentioned 18, whatever that percentage is, it's an essential part for decarbonisation. Making it a level playing field would also be useful, because I mentioned, sure, you can look at society today and say, well, you know, gasoline's most efficient, and why would anybody change? Well, gasoline is actually a direct contributor to global warming. So we have to move away from that. So we shouldn't be subsidizing those solutions anymore, and we should actually be enabling, through carbon pricing, etc., new technologies that humankind needs to actually become more economical. That's the point here. We can't stay where we are. You know, I haven't heard many solutions to the alternative. We've got direct electrification, we've got hydrogen, and hybridization with batteries and storage. That's what we need to deeply decarbonize society. And it's not a Ceres Power point of view, it's a global point of view. You've got 30 governments globally all going down this path. You've got trillions of dollars now flowing into investments in these areas. So I think it's going to happen. I'm optimistic for the future.
Thank you very much, Phil, and thank you. And over to you, Paul.
I'll give you I'll give you my answer. It's really straightforward. So what you need is you need to make dumping stuff into the atmosphere cost something, and not just a little. It needs to cost a lot. We have to stop treating the atmosphere as a public sewer for the effluent of fossil burning, and that includes the fossil burning that's done in order to make hydrogen right now. We also need to make sure that when we do that, when we put a price on carbon, that's substantial, sustained, growing, and bankable, so that it's worth making giant investments in capital to avoid emissions. We also have to tax or tariff the goods from cheater or laggard nations like the United States to ensure that they don't get a trade advantage. The third thing that we have to do is we have to put emission bans in place in major cities. And by so doing, we have to actually start valuing human lives that are cut short by the toxic emissions from the current fossil paradigm. And the very last thing that we need to do, the thing that we must not do, is we must not bet on individual technological winners and losers as governments with giant amounts of tens of billions of dollars worth of subsidy. If you put in place those policy measures, carbon taxes and emission bans, the market will do what it's good at, which is it will allocate capital to solutions that work, and it won't allocate capital to solutions that don't work. When you do that, you're going to get transport electrified, not switching to hydrogen. If you subsidize hydrogen, you'll get black hydrogen rushing in to fill the vacuum because there's no green hydrogen to supply those trucks or trains or aircraft. And as a consequence, you'll actually get distortions of the market that are not actually valuable to decarbonization, which, by the way, are of quite some interest to some people that actually derive their income from fossil fuels right now. Okay. And as a consequence, we have to be careful about what the incentives generate, because perverse incentives generate perverse outcomes. Put in place the policy measures that stop treating the atmosphere like a public sewer. And by the way, that includes taxing methane emissions at 86 times their equivalent in CO2, which is what methane is equivalent to in global warming potential relative to CO2 on the 20-year time horizon, which is the relevant time horizon. And if you do that, you will not get these perverse outcomes. That's what we need to do. And we shouldn't be betting on tech winners or losers. If hydrogen comes out on top, fantastic. That's great.
Thank you very much, Paul. So that draws to a close our discussion and our speakers. I'd just like to say thank you again to Phil, Wayne and Paul for a very engaged and really positive dialogue. And thank you very much indeed. Thank you. Thanks, everybody.
Thank you very much.